In this video, we will look at the complex Fourier series. Now, as we know, periodic signals can be represented by adding together sine and cosine functions. However, it's often more convenient mathematically to use complex exponentials, and we'll explain in this video how that is done. But also, more generally, if you are interested in complex valued functions, then the standard Fourier series won't work for you. You'll, in that context, need the complex valued Fourier series, in other words, the complex Fourier series. This will also introduce the concept of negative frequencies as well as positive frequencies, and so we'll get into that in this video as well. So there on the top of the slide is the standard expression for the Fourier series. We're basically saying that a real periodic function can be expressed as a constant offset term, cosine 0, multiplied by a0, plus an infinite number of cosine terms of increasing frequencies from 1 to infinity, plus an infinite number of sine terms with increasing frequency from 1 to infinity. And we'll be showing that that expression is identical to the complex Fourier series, which you can see here is a very compact form. And when we derive it, as I also just mentioned earlier, it will then also be applicable to when f has a complex value rather than just a real value in the top case. But it's important to note that when this is a real periodic function, which is a lot of the time, depends on your application, but a lot of the time we're dealing with real periodic functions. And so it's important to remember that this left-hand side, if it's real and periodic, then that right-hand side, even though it's got an infinite number of complex exponentials here with complex coefficients as well, nonetheless, it all adds up to being a purely real periodic function, if indeed your left-hand side is a real periodic function. So let's get into the derivation, and we're going to make use of these expressions, which I've derived in another video, just saying that cos x is equal to a sum of complex exponentials divided by 2, and that sine x can also be rewritten as a difference of complex exponentials with this corresponding multiplication by minus I over 2. So we'll use those expressions just by directly substituting into the standard Fourier series. So we'll replace the cosine, in fact we'll replace the 2 cosine by that sum of complex exponentials, just again substituting from the previous expressions, and likewise the 2 sine here will be replaced by the minus I and then the difference of those 2 complex exponentials. Then for the next line here, all I've done is recognize the fact that here we've got the e to the in omega naught t term, and also over here we have the same e to the in omega naught t, and I've just put that here and recognized its coefficients are an minus ibn, so I've grouped them there. And then for the negative argument of the complex exponential, which appears here twice, I've just grouped that into one single term there with a coefficient of an, and then minus gives plus ibn. So this is just grouping the terms, rewriting quite straightforwardly. So that's the same expression, just given at the top of the slide there. So 2 observations about that. The first is that we now have a complex number as a coefficient for each of these frequency terms. And so this first one I'll call Cn, and then the second one we can see it's just the complex conjugate. And the complex conjugate means you just negate the imaginary component. So if it's minus ibn, for the complex conjugate you use plus ibn. The second observation is that we now have both positive and negative frequency terms. So the positive frequency terms are clearly these ones here where we have a positive coefficient. So we've got n omega naught as a positive coefficient of time. And these all have these coefficients Cn. And then over here we have a complex exponential now with minus in omega naught t. So we've got a minus n omega naught as the coefficient for time. And so the frequency is like the multiplier for the time variable. And so now we've got a negative multiplier. And so we'll see what that translates to as we go on in this video. Okay, so let's take a look at one of the components, one of the positive frequency terms. So that first summation we saw on the earlier slide. Let's look at an example, e to the in omega naught t. What is going on there? Well, we know by Euler's relation, of course, so that's just given by cos plus I sine of the same argument. We've got a real part and we've got an imaginary part. So we could just plot that on an Argand diagram or a complex plane. But we make immediately the observation that here t is our independent variable. So these real and imaginary components are going to be changing with time. So that means we've got a time changing or a time varying complex number when we have this e to the in omega naught t. So what we're going to do is for time t equals 0, that's a nice simple case to pick. I'm just going to plot it on the complex plane. The Argand diagram. So when t is 0, this imaginary part disappears, and we're just left with a cos of 0, which is 1. So I've just got a value of 1 on the real axis here. So just drawing a line. This is again the phasor notation or description, where we go from the origin to the point of 1 on the real axis. Now, so I'm just again showing there that's the real part, and here there'd be a 0 imaginary part at time t equals 0. Then we make the observation, of course, that as time increases, so t greater than 0, then obviously we're going to get components. We're going to get a positive value initially of the cosine. That will start to decrease. And then the sine term will also now kick in as well. That'll take on a positive value. And what will happen then is that this line will start to move. In other words, that point in the complex plane for that complex number will now shift, it will now change according to the moment in time t. And we can see it's going to go in this direction because the sine here is a positive function initially, and the cos stays positive as well. So we're going to go in that direction. So that's why I've indicated the positive frequency direction. So this is showing it now. I've just used something from Wikipedia here for this animation. I've just rearranged it a little bit, and you can see here now that we've got effectively that complex number changing with time is tracing out this circle. So it should be no surprise, of course, that the real part, in other words, just projecting that line back to the real axis, is just tracing out a cosine function. And so that's exactly what we see here. And then the imaginary part, of course, as that progresses in time, is tracing out a sine function as shown on the left-hand side there. So hopefully you can see that a time-varying complex number in the form of e to the in omega naught t is tracing out a circle in the Argand diagram or the complex plane. So that's what a positive term, a positive frequency term will do. For the negative frequency term, so now we're just looking at e to the minus in omega naught t. Again, using Euler's relation, just express it as cos minus I sine now. We can plot that also in the complex plane. And again, at time t equals 0, we still get that position of 1 along the real axis only. And now, as we advance in time, as that variable t increases beyond the value of 0, we can see that, again, the cosine part, the real part, is going to stay positive. We know what the cosine function looks like, so it starts at a value of 1. But with time, that will, again, decrease, just like it did in the previous example. But now, this imaginary part is now minus sine n omega naught t. So that means we're not going to go upwards with time, we're going to go downwards with time. So that means this negative frequency term corresponds to a clockwise circular movement. And that's really the key in understanding negative frequencies, that really we're just flipping that imaginary part, and so that means that we get this mirroring in the real axis, which means if we've got a positive frequency that's going in an anti-clockwise direction, when we look at the negative frequency, we have a phasor tracing out a clockwise circle. So let's take a look at that now. This is the real component, which looks identical for the negative frequency as for the positive frequency, because cos is is an even function. And then now the crucial difference being that because this is tracing out this clockwise circle with time, so you can see here that as the phasor hits there, we're there tracing out, you can just see it there, that negative sine wave. Hitting 0, we're tracing out there a negative sine wave you can see on this plot. Okay, negative again there. So therefore this negative frequency direction is this clockwise movement. And again, just to make the note therefore, the only difference compared to the positive frequency term is that we've got this negative here, which effectively is mirroring in that real axis. Okay, so our expression so far in deriving the complex Fourier series, that's where we'd got to. So we had a complex number multiplied by the positive frequency terms, and then we have Cn star, the complex conjugate for a coefficient for the negative frequency terms. So what we'll do now is we'll just look at one frequency, in other words, one particular integer value of n, because that's going to be a multiplier of n omega, so n omega 0, that gives us a frequency. Let's just consider one frequency and visualize what is going on there. Okay, so first of all then we've got what we've previously seen. We've got the time-changing complex numbers tracing out those circles on the complex plane. So those two guys are quite easy to understand. But what do these multipliers do, these coefficients? Let's take a close look now at what's changing there. So there's our familiar positive frequency term. As time progresses, it just moves that complex number around on the complex plane in this phasor kind of description. Positive frequency direction, remember, is anti-clockwise movement. Now, what happens if we multiply that by a coefficient Cn? Now, remember that Cn is a complex number, and so what we had derived by grouping those terms was that it was an minus I bn. So here I've plotted the complex number for time t equals 0. And so that means this part here will just be equal to 1 at time t equals 0, which means that when we plot Cn, we can just plot that directly because the complex exponential is equal to 1. Okay, so it's 1 times that complex number Cn. And so what we're going to see is that if that's the complex exponential there at time t equals 0, then this Cn as the multiplier is just going to give us Cn. It's giving us what I'm going to call a phase shift and a change of magnitude. Okay, so the complex exponential is going to have a phase shift first of all, so it's going to move by some angle, and then it's going to increase or decrease in magnitude. And what I mean by that is simply that, if this was just the complex exponential at time t equals 0, it's just a value of 1 on the real axis, then obviously at time t equals 0, this whole expression is just the plot of the complex number Cn. Okay, so instead of that complex exponential being by itself, if you like, with a coefficient of 1 just sitting there, by multiplying it by Cn, we've turned it into a plot of just Cn, that complex number. And then we know that because it's being multiplied nonetheless with that complex exponential, which is changing with time, that therefore this is going to be moving in an anti-clockwise direction as that complex exponential takes on non-trivial values of time. So you can see, again, I'm pointing out at time t equals 0, we just have Cn as that is equal to 1. And so Cn is just an minus ibn, giving us that point on the complex plane. Now, as we let the phasor do its stuff, in other words, as we let time unfold, then that is going to progress in that anti-clockwise direction, which we'll see in a second. So here we are then, as mentioned, that as time now unfolds, that complex exponential will now trace the circle, but now it is multiplied by that complex coefficient, that Cn. And so the net result is what I'm animating on the slide here, just showing that we still get that circular motion, but now the complex number has increased or decreased in magnitude according to Cn, and it's also got a phase shift relative to the origin in time. So it's no longer kicking off directly from the real axis. It's now initialized from this phase shift away from that real axis. Okay. Right, so with the negative frequency term, we have a similar situation. There's the complex exponential for minus I and omega naught t. We've looked at that already, and it's just this unit circle being traced out by that complex number. Now we're multiplying it by Cn star, just the complex conjugate of Cn. And again, this is the complex exponential at time t equals 0. It's just a value of 1 on the real axis. By multiplying by Cn star, we get, first of all, a phase shift and then a change in magnitude. So this is just the origin here, and we're just plotting here Cn star, for which the magnitude of that direction, that line, is just obviously the magnitude of Cn star, and it's at an angle phi to the real axis. So all the basic expressions apply. Distance an on the real axis, distance bn on the imaginary axis, and again at time t equals 0 I had the exponential equal to 1, which meant we just plotted Cn just at that point there. And then as time unfolds, that complex exponential moves away from a value of 1 and starts to take on the familiar Euler relation. It's just using the cos and the I sine, or in this case minus I sine, which is why it now goes around in this clockwise direction. So again, think of the coefficient for the negative frequency term as just taking that unit phasor, if you like, and just scaling it up and giving it a phase shift. Okay, that's all we're doing with the complex coefficient there. But another key point to note here is that the coefficient, Cn star, we can express, obviously it's an plus ibn, but we can make the observation, comparing it to the previous slide, that it was just the coefficient for minus n. In other words, for the negative frequency. It's doing exactly the same as what we saw for the positive frequency, but just now going in the other direction. So that will be clarified still further here. This is the positive frequency with the coefficient. This is the negative frequency with its coefficient that I'm now labeling as C minus n. And you can see from this figure that it is rightly labeled as C minus n. So here was the original an minus ibn, this lower line here. That was the coefficient Cn, which is going to be moving in that anti-clockwise direction because it's driven by that complex exponential changing with time. And then the negative frequency is just mirrored, and that's going to be moving in this clockwise direction. So you can see these are kind of, they're just reflected in the real axis. And then all the usual expressions apply, just looking at basic trigonometry. So feel free to pause the video and take a closer look at those trig identities applied to these triangles that are being traced out by these two complex numbers. So let's now see what happens when we add together both the positive frequency and the negative frequency. Again, I'm really focusing here, I must say, for the case of real periodic functions. And in that context, we're getting the following, where as we take the positive frequency term, we multiply it by Cn. So that's taking us from the origin to here. And now we're adding on that negative frequency component with its coefficient C minus n. So remember those two complex numbers you've just seen in the previous slides, the Cn and the C minus n. Well, I'm just doing the first one, and then I'm adding on the second one. So you can get some insight into this more if you take a look at the video I did on Euler's formula and the expressions for sine and cosine. So this is very similar to the kind of plots I did there. So now we're coming out here and then back in, and so at time t equals 0, we're just getting 2an along this axis. Okay. And then obviously with a general moment in time, this sum of these two exponentials, the positive frequency and the negative frequency, when added together, will always, for a real periodic function, which is where we started from with the basic Fourier series, the standard Fourier series, will always deliver something that's changing only on this real axis. Okay, so that's the example I'm giving here. This is derived from a Wikipedia animation. And so what I'm showing here is that our time-changing complex number that we're getting by adding together this to this, there was the positive frequency and the negative frequency with their respective coefficients. When you add that all together, what you end up with is just something that is moving only on the real axis. Of course, provided that the original function that we were expressing as a Fourier series was a real periodic function, which a lot of the time it is. You may also see in other popular videos that we can also trace out all kinds of different patterns, and that is true if you have a complex valued function. Okay, here we've been limiting ourselves to real valued functions, which is why when we add together these two frequencies, the positive and negative frequencies with their respective coefficients, we only end up with something that's moving along that real axis only with time, which means we're tracing out a real function, a real periodic function. Okay, and so that's what I'm observing here. If you applied this expression, we're almost there with the complex Fourier series, if you applied it to a complex valued function, then this could go anywhere on the complex plane, not just constrained to the real axis. So to summarize, the top expression is hopefully very familiar to you, saying a real periodic function is given by an offset term plus this infinite set of cosines and infinite set of sine terms. And then by using Euler's formula, we can substitute for cosine, substitute for sine, and then we end up with this middle expression here where we've got the constant offset term, then we've got positive frequencies given here with their complex coefficients and negative frequencies with their coefficients c minus n. And what you should be able to see is that we can combine all three terms into just one. So first of all, look over here. We could extract that negative factor here and put it into the summation. So if we had n going from -1 to minus infinity, or indeed minus infinity to -1, then we could have here Cn and e to the in omega naught t, which is identical to that term there. So these two can be completely combined if we just run n from minus infinity up to plus infinity. And of course, in that integer stepping of n, we're also going to pass through 0, which is exactly what we need because we need to include that term a0 as well, which has a coefficient of exponential, and where n is 0, exponential of 0 is 1. And so a0 is also included when n equals 0 in that expression. So very compact, I'm sure you would agree, compared to the original expression. And now it generalizes for complex valued functions as well. Just to point out how we find the coefficients for those expressions. Well, for the standard Fourier series, we know the approach. You take the real periodic function, multiply it by the term for which you wish to find the coefficient, do the definite integral, and normalize by the range of integration. That gives you an. Same approach for bn, the coefficients for the sines in the standard Fourier series. And then the amazing thing is the same approach applies for the complex Fourier series. You take the periodic function, which now in general could be complex valued, but a lot of the time we'll be dealing with real functions only. So you take the periodic function f of t, you multiply it by the term for which you wish to find the coefficient. Now, there is a little qualifier in here. The term for which we wish to find the coefficient is actually e to the in omega naught t. Now, to find the coefficient for that, we need to multiply it by e to the minus in omega naught t, because that will give a net result of 1, which is what we want. And obviously, if you multiply e to the in omega naught t by e to the minus in omega naught t, you get e to the 0, which is a value of 1, which is what we want. We can go into that more in another video. that is how you calculate the coefficients for the complex Fourier series. It's basically the same approach. The only catch is you do need this negative in here in order to pick out the correct complex exponential, the e to the in omega naught t. And when you've done that multiplication, you do the same thing. You sum up the function and then divide by the range of integration, and that will give you that coefficient Cn for the e to the in omega naught t. Okay, so in summary, signals can be represented by summations of sines and cosines. Alternatively, we can use complex exponentials with both positive and negative frequencies. It's more compact, mathematically convenient, and allows us now also to consider complex valued functions if that is what we want to do. Thanks for listening.